Wave functions? Today's question, we're going to talk about the wave function and its importance to quantum mechanics in the realm of wave mechanics. The problem asks us to consider the wave function capital Psi of x and t, which is equal to a e to the negative lambda absolute value x times e to the negative I omega t, where a, lambda, and omega are positive real constants. Part A, normalize this wave function, and B, determine the expectation values of x and x squared. Good thing we've seen those before. Part C, find the standard deviation of x. Sketch the graph of the wave function squared as a function of x. And mark the points expectation x plus sigma and expectation x minus sigma to illustrate the sense in which sigma represents the spread in x. What is the probability that the particle would be found outside this range? We're going to have to use some clever math on that, so stay tuned. Alright, so for our solution, let's first rewind back to the last question that we covered. Remember that probability has to sum to 1. So this concept of normalization is going to play a critical role, but now instead of being given a probability distribution, we made one out of the wave function using what's called the magnitude squared. And that's what we see in this first integral. The wave function magnitude squared. The thing to notice about magnitude squared is that in complex variables, this means that we're multiplying the complex conjugate by the wave function itself, and that's what we see in the blue and green in the next integral. That asterisk or star represents the complex conjugate in this context. What that means is that we change the sign on any imaginary part, and then we multiply through and let the algebra work its way out. What does this look like? Well, in our next step here, we plug in the wave function after taking the complex conjugate. You notice that the real parts remain unchanged, so a e to the negative lambda times absolute value x, that's unchanged. But this exponential here with the omega term has a positive sign, versus the green case, which has a negative sign. After this, once we make sure we have that step done, because again, we need a magnitude, so we're not worried about the directionality that the imaginary part gives us, we're just worried about how big it is. And that's why we multiply by the complex conjugates, and what we see in this next step is because it cancels out the imaginary parts. Notice that a times a, both being real, we just get a squared, and we move that to the outside of the integral. And then we just use the, once we distribute everything and multiply across, we use the exponent rules to add in the powers of the exponents. So we see we get a negative lambda and a negative lambda, they add together. But what we see is that positive I omega t minus I omega t, those cancel, and e to the 0 is just 1, so it goes away and it vanishes. So we don't have to worry about any phase factors, so to speak, in these calculations. What's cool about this, though, is now we can just focus on the real parts and evaluate what they look like. I'd also like to take a second to note that this negative infinity is red due to the fact that we know that this distribution is even, and with that being said, we cannot take the integral of an absolute value, we have to split it up into a piecewise definition. But why do that when we have an even distribution and we can just double it at the cost of an infinity? So this negative infinity gets doubled, and that's why we have a 2 here and a 0 there in the next line of integration. Also note that we dropped the absolute value on x because we're taking the positive side of that expression, or rather the domain, so the expression x is positive there, and we just use that instead of the absolute value. Now that we have this, a quick u sub can knock out this integral, and that's what we see here. E to the negative 2 lambda x over negative 2 lambda. The 2 from doubling the integral and the 2 in the denominator here cancel out. Wonderful. And then we evaluate the integral. So we have a squared e to the negative infinity minus e to the 0 over negative lambda. Wonderful. Easy enough to deal with. what we see is that the characteristic, this being an improper integral, of course, the characteristic of e to the negative infinity goes to 0, and that's what we end up with here. And then, of course, e to the 0 is 1, so 0 minus 1 gives us negative 1 over negative lambda. Negatives cancel, as you see highlighted. And so we're stuck with a squared over lambda. But remember, we are normalizing here. So this a squared over lambda is actually equal to 1. That's what we started with. Now solving for a, we multiply over the lambda and then take the positive square root. And here we are. The normalization is by a factor of square root of lambda. That's wonderful. Now let's see how we can apply this elsewhere. Okay, so now that we know we have a normalized wave function, which is a necessity, go check out the notes I've prepared on why normalization and what it means with the wave function, and come back if we have questions. But now we need to apply the expectation values, or rather we need to apply this wave function normalization and complex conjugate carryover to expectation values. We'll start with the expectation of x. We've seen that before in the last question when we had a probability distribution. Now what this looks like and what is going to be critical to understand moving forward is that for these continuous variables, the expectation value might be an operator and those need to act on a wave function. So while we can multiply x by the probability distribution, psi squared, magnitude psi squared here, what it actually represents, and I think what is the more formalistic approach, is psi star times whatever you want the expectation value of times psi without the complex conjugate. And we'll see once we get into the expectation value of momentum why that's important that we set it up this way. And also this gives a little more carryover into the matrix mechanics side of things. So keep this setup in mind more than this one. With that being said, we use the same integral tricks that we had last time. We had an a squared out there, the imaginary parts cancel out, and we're left with e to the negative 2 lambda absolute value x multiplied by x. What's cool here is that that multiplication of x makes this an odd integrand over symmetric bounds, odd integrand, symmetric bounds, and we know that those evaluate to 0 because of the cancelizing that they have. Wonderful time-saving trick there. Now we'll get on to the expectation of x squared. And again, this is a probability density notation way of writing it. This is an actual mechanical way of writing the expectation, which will, again, we will see the importance of that soon, I promise. But again, you see psi star, psi, knowing the fact that x made it an odd function, if we multiply by x squared, even times even is an even function. So we're going to use the red limit trick again to double it, but put at the cost of an infinity and put a 0 there. And you see we have x squared e to the negative 2 lambda x. And so now what we can do is again form match with one of the integrals in the table that were given to us in this book. The integral in the book reads 0 to infinity of x to the n e to the negative x over a dx, and it's equal to this result. So our goal now is to determine what n is and what little a is, and then evaluate this integral using this notation with the parameters defined. Let's find out how to do that. Much like we saw in the last question, we have to match forms with the integral table to the integral we have. So if we match the x variable, the table gives us x to the n. What we have in this context is x squared, so that gives us n equals 2. Cool, easy enough. Here, for matching the e to the negative x's, or the exponents, we have 1 over a, the arguments of the exponents. In the form, we had 1 over a, and in the integral we have for the problem, we have 2 lambda. So if we solve this for a, we get a is equal to 1 over 2 lambda. If you have questions on the form matching, just shoot me a message and we'll get it squared away. Take it step by step. But this is a great way just to fast forward the process because these questions do become lengthy after a while. So with that being said, we're going to move on to evaluating the integral with these parameters. Recall that we had 2a squared positive integral to positive infinity x squared e to the negative 2 lambda x dx. Here, we plug in the form. Remember, we had n squared times a to the 2, or rather a to the n plus 1. So n being 2 gets put here and here. A gets in the bracket. And we see that we have a squared here, but we know from part A what that normalization factor was, which was the square root of lambda. And so we plug that in here as we're simplifying this expression out. And then you see we get 2 lambda times 2. That gives us 4 lambda. Meanwhile, we have 1 over 2 lambda cubed, so we get 8 lambda cubed in the denominator. So clearly a factor of 4 and lambda will cancel out with a factor of 4 and lambda in the denominator, thus leaving us with 1 over 2 lambda squared. Pretty easy there, nice and straightforward. Now for part C, we wish to find the variance and the standard deviation from the variance. Recalling that the variance, sigma squared, is equal to the absolute value of x squared minus the expectation of x squared. Excuse me, let me try that again. The variance, sigma squared, is equal to the expectation value of x squared minus the expectation of x squared. Okay, the square of an expectation versus the expectation of a square, two different things, but they get rattled together. Nonetheless, you plug everything in that we found, expectation here, expectation there. Wonderful to see the expectation of x be 0 because it makes the calculation easy. And thus we land with a sigma equals 1 over square root of 2 lambda. So our variance and standard deviation both depend on that factor of lambda. And that will make a difference whenever you look at a graph of these things. So speaking of graphing, let's now move on to kind of part C of this thing and look at what we're actually trying to settle down with these things. Meaning what we're looking for and so on and so forth. For the graph, the x are points at 0 plus sigma and 0 minus sigma, so plus or minus. Okay, thankfully that our expectation of x, the average is at 0, the whole graph is centered at 0, so that makes sense. It works out well. So the height of these points are found to be, well, the wave function is a function, so we can get the magnitude out of that by plugging in the point x. So here we see we plug it in. The absolute value here squared gets rid of that time component that we had before, and it's just a positional component here. So we get a squared again, e to the minus 2 sigma lambda. Again, absolute value knocks them out, no worries there. And then you plug all the factors in. We had the sigma was equal to 1 over square root of 2 lambda anyways, so that cancels a factor of lambda, nice and easy. And then 2 over root 2, if we rationalize that, we just get a negative root 2 there. That's how we find that. But e to the negative root 2 is equal to this decimal times lambda, of course. So again, you see that this free floating parameter or free variable lambda plays into all these things. And this because this is an even wave function, an even distribution rather, there is a symmetry here. And the symmetry of this density, which is centered at 0, helps in a probability calculation. So again, it being we would have to find the probability by measuring two integrals, one on either side of lambda, or excuse me, of sigma, or we could just find one of them, one area, and double it. And that's what we do here. This is what I mean by use symmetry. We have this area to calculate and this area, but since we are an even probability distribution, it's the same as cutting that in half and doubling it. That's why we have a 2 here and only one set of that domain. Once we plug that through, we get the integral expression here. I think we've seen enough of these. Again, once we plug sigma in, we get this cancellation, and again, we get e to the negative 2, e to the negative root 2, which is equal to 0.2431. For the graph itself, I've composed another little animation that I'll put in another part to show you how the varying lambda changes the order of this thing and what exactly I mean by probability of outside sigma. But a pretty good exercise, and I think that this one's going to pay off dividends because of the e to the negative I omega t. That part will come back later in this book, and we'll have a lot of fun. Okay, fun is subjective, but it's a lot of fun to learn had to deal with both the time and the position coordinates. So with that, I will see you on the next one. Later.